So good afternoon, everybody. I hope you are able to see the screen. Are you able to see the screen?
Yes, ma'am.
Okay. So just starting with just a recap of what we did yesterday. We yesterday saw the concept of field lines. Field line representation is simply a pictorial representation of how the field would look around a source charge, or a combination of or a collection of charges. And we have seen that field line distribution, the field line especially, field line is distribution talks about what is the direction of the electric field at a point, and also pictorially tells you where the magnitude is larger and where it is zero and things like that, or how the direction of the electric field changes around a charge distribution. And in that context, we have seen some very important charge distributions. The first was a uniform charge distribution. Uniform charge distribution is denoted by parallel equispaced field lines. And then we saw how decreasing electric field, like let us say I'm talking about an electric field which is large here and smaller as you go up. So that is represented by field lines which are diverging. That means when the lines are going to become farther away from each other, then you know that in that location the field is smaller. Then we have seen what is the field for, how the field will look for a point charge, positive or negative. It will be radially out or in, as the case may be, whether it is positive or negative. And then we talked about a disk, a uniformly charged disk. Okay, then we have seen that if this disk is uniformly charged and positive, then the field lines will be uniform and out of the plane, perpendicular to the plane on both the sides. And then, of course, we have seen for a dipole how the electric field looks. Similarly, for pair of identical charges, how the field will look. Okay. Then once we were done with that, we have quickly gone to what happens to a charge placed in an external field. Till now, we were looking at what is the field due to a charge. Now what we are doing is, we are not bothering about who has created that field or what has created the field. We know there is a field. Now when you put a charge there, what happens to the charge? We have seen that the charge will experience a force. The charge will experience a force equal to F is equal to Q into E, and we worked out a problem which is simply your E by M measurement by Thomson's J.J. Thomson method. So this is the numerical we have done in the last class. Today, similarly, we'll see another very important calculation. Okay, so this is talking about again two plates. You have two plates, 1, 2, and the length of the plate is L. The length of the plates is L, and they will carry equal and opposite charges. They carry equal and opposite charges such that the field between the two. Now look at this, guys. If this is a positively charged plate, okay, what will be the direction of the field here in this region? What will be the direction of the field? Where I am marking. What will be the direction of the field? Downward or upward? What's the direction of the field?
Outward.
Outward. Downward or upward? It will be perpendicular to this sheet. It's not a line, it's a sheet. Sheet. Okay? Will it be downward or will it be upward?
Downward, ma'am.
Downward. Because please remember, field is always going to be away from a positively charged body. It will be uniform and downward. Okay, so let's call this field as E plus. What will be the field because of a similar negatively charged plate? In between these two, what will be the direction of the field due to the negatively charged plate? Will it be upward or downward?
Upward.
Upward. This is a negatively charged plate. Uniform field is downward. It will be downward. It will be downward. Okay, so you're just going to have fields which are adding up. Or you can say that if you have two plates carrying equal and opposite charges, there will be a uniform field coming from the positive towards the negative plate. Okay, and in the last class we have seen And please, the condition is that this gap should be very, very small. The gap should be very small when compared to the area of the plates. And we have seen that the field due to the plus plate is going to be sigma by 2 epsilon naught. And field due to the negative plate is also going to be sigma by 2 epsilon naught. So both of them will add up and give you sigma by epsilon naught. So that will be the field between two, note down, the field between two parallel plates carrying equal and opposite charges will be sigma by epsilon naught. What is sigma? What is sigma?
Surface charge.
Surface charge density, charge by area. Okay, so this is going to be the field. So now keeping this in mind, let us look at this problem. So in the picture below, there are two plates of length L. Okay, one is carrying positive charge, the other is carrying negative charge. I immediately know that the top plate is positive and the bottom plate is negative because my field is given like this. Okay, now it says that there is a charging unit. From the charging unit, a particle, an ion, okay, an ion of mass m equal to 1.3 into 10 to the power of minus 10 kg and having a charge, negative charge, 1.5 into 10 to the power of minus 13 coulomb. So the mass is 1.3 into 10 to the power of minus 10 kg and the charge it carries is minus 1.5 into 10 to the power of minus 13 coulomb. Okay, this enters into this uniform field. And where is the uniform field? A uniform field is there everywhere starting from here to here. So in this region, this charge particle is entering. So when it enters the charge particle, when the charge particle enters this region, okay, it is meeting the field. It is meeting the field. So the field direction is this and your charge is negative. So what will be the direction of the force it experiences? What will be the direction of the force it experiences? F is equal to Q into E. Okay, Q is negative. Therefore, the force it experiences will be in the upward direction. The force it experiences will be in the upward direction. But please remember, this charge particle is actually moving like this. It has got emitted from here and it is moving along the x-axis. But then it is experiencing a force in the upward direction. So what will happen to it? Along with the x-axis movement, there will also be a movement in the y-axis direction. Therefore, it gets deflected like this. Are you understanding this? It will move along the x-axis, but at the same time, there is also a force pushing it in the upward direction. Therefore, what will happen? It will be a combination of both this. Therefore, it gets deflected like this and moves like this. Is this point clear to you? Are you clear or not? If you have a doubt, please ask me what it is.
Clear, ma'am.
Clear. Okay. So now, what you're supposed to do is the mass is given, charge is given, and the deflecting plate, it is entering with the speed 18 meter per second. So let the initial speed be 18 meter per second before it is entering. Okay, and the value of the electric field is given as 1.4 into 10 to the power of 6 Newton per coulomb. So what is asked is, how much is this vertical displacement? What is the vertical deflection of this drop at the far edge of the place? That means when it reaches here, what is the displacement in the upward direction? How much did it get deflected? Okay, so this is the problem. So now you have all done in your intermediate, you must have all done projectile problems. Yes or no? Have you done projectile motion? Sound seems to be traveling very, very slowly from me to you. It's taking at least 5 minutes. Have you studied projectile motion? Okay,
Yes,
no
ma'am.
point. Yeah.
Yes, ma'am.
Now look at this. If this charge particle is entering along the x direction, is there any acceleration or force? Along y direction, yes, you know there is a force. But along the x direction, is there any force? Nothing, no, it is just entered. So,
No, ma'am.
so now it's going to stop it from moving in this direction with the same velocity. But then there is an upward force, therefore it is going like this. So if I take just the x component of the velocity, then the x component of velocity will not change. It will be V naught only. Okay. And another thing is, let t be the time taken. Let t be the time taken to cover the distance L. Okay, then we can say that L will be equal to V naught into T. Are you convinced? Are you convinced? Because it's a constant velocity. Along the x direction, the velocity is a constant. Okay, therefore, it's going to move with the same speed only. Therefore, L will be equal to V naught into T. If T is the time taken to cross. Okay, so now you got this. Now, along the y direction, what is going to happen? Let us see what's going to happen along the y direction. Along the y direction, what happens is, I made a small mistake. I should not mark this entire distance as y. Y is only, what's happening? Not responding. Yeah, y is just this distance. This is y. Okay, that much it got deflected from the x-axis direction. So you have to find out y. Okay, so let us also now see how to calculate y. So we can also say y equal to half a t square. Why am I saying y is equal to half a t square? Anyone?
Initial velocity along the y-axis is 0.
Very good. Initial velocity along y-axis is 0. Therefore, s is equal to ut plus half a t square. I'm just going to use that. Okay, so I can say y is equal to half a t square. And I can do one thing here. I can write half into, how do I write my acceleration? I know that F is equal to m into a equal to q into e. Right? So instead of a, what will I do? I can write QE by m. Is this step clear to you? So instead of acceleration, because after all F is equal to m into a, that's from mechanics, that's equal to q into e. Therefore, I can write acceleration is equal to QE by m. And then of course, I have my t square. Let me call this equation as 1. Let me call this equation as 2. Now, I don't know t. I don't know t. But I know V naught, I know my L. I know my L, I know my V naught. So, can I not eliminate my t square in equation 2 by using equation 1? So, what we can do is, let us try to do that. Yeah, so that's what I've written here. So, we can get rid of this t. We can get rid of t square. So, let me just write it. Y is equal to, just now I wrote, it is going to be q half QE by m into t square. Instead of t square, what I will write is l square by v square. So just by using t is equal to l by v. L by v. Just by using it in this equation, we are able to get this. So what you now need to do is just substitute for q, because you already know charge. You know what is a field. You know what is the mass of the particle. You know what is L. You know what is the velocity V naught. So put everything into the equation. Once you put everything into this equation, you will get the answer. You will find that the deflection is actually 0.64 mm. Okay, in case you're wondering why we have discussed this particular problem, okay, This problem is also something that you will come across if you were in the lab. You would have come across this lab in this particular experiment. This experiment was also going to be used to measure the specific charge E by M of an electron. Could be measured this way. Okay, so there what happens is, no, the first part of the thing is what is discussed here. Then the next part will be discussed in magnetism. When we do magnetism, there I will discuss the second part of this particular equation. And then you will understand how this setup could be used to find out E by M of an electron. Okay? Now, today's class is not going to be a long one, it's a short one. We'll be finishing this chapter. Okay. So, sometime back, I think 2 classes back, we talked about what is a dipole. A dipole is a molecule where the molecule is going to behave as if there is a positive and a negative charge separated by a distance d. And we talked about what is called the dipole moment. Dipole moment is q into d. And we have seen that the unit is coulomb meter. The next thing we have seen that it is a vector. And what is the direction of the vector? The direction of the vector will be from the negative charge to the positive charge will be the direction of the p vector. That's what we have seen. Okay, so now what we'll do is, in the previous classes, we treated the dipole as a source. The dipole was a source of electric field. And we found that the electric field was falling off as 1 by cube of the distance. But today, we are doing the opposite. We are taking a dipole, we are going to put it in an external field. Somebody else has created a field, electric field. We take the dipole and put it in that electric field and find out what happened to the electric field. Just like few minutes back, we have seen what happens to a point charge when you put it in an external electric field, in a uniform external electric field. Those were the 2 problems that we have done over yesterday and today. So today we are going to see what happens if you take a dipole and put it in an external and a uniform electric field. So let E be the electric field. And so here is your E. It's uniform field. So we are drawing a series of parallel lines and representing the uniform field. And then we put our dipole here. And the only thing we are doing here is we are going to make the dipole, make an angle theta with the electric field. Look at the P vector. The P vector is from the negative charge to the positive charge. And it is going to make an angle theta with the E vector. Now, let us see whether this dipole is going to experience a force. We have seen how the point charge was experiencing a force. F is equal to Q into E. Similarly, let us see whether the dipole will experience a force. So look at this negative charge. What will be the force it will experience? It will experience a force opposite to the field direction. F is equal to Q into E. Similarly, when you come to the positive charge will experience a force F is equal to Q into E parallel to the field direction because it is positive. And you will find that these 2 field forces are equal and opposite. Therefore, you come to the conclusion that the net force acting on a dipole is 0. The net force acting on the dipole is 0. So you can just close your eye, generalize this result and say that when a dipole is placed in a uniform electric field, then the net force experienced by the dipole is 0. Okay? But at the same time, notice one thing. Net force may be 0. Net force may be 0, but you can see that this force is forming a couple. Do you know what's a couple? What's a couple? Couple is not a boy and a girl. I'm talking about the physics couple. Can someone answer what's a couple?
Forces acting opposite, which are equal.
Two forces which are equal and opposite constitute a couple. Fine. Okay, now you just look at this. My left hand is exerting a force on the right hand is exerting an equal and opposite force on the left. Is this a couple? Is this a couple?
Yes,
Say yes or no.
Yes, ma'am.
Yes, you are saying. Okay, who said that?
Kiranmay.
Kiranmay. Okay, now I have another situation. So here is an object. I'm going to apply a force like this. Okay, my finger is exerting a force like this. Another finger is going to, or I'll say my hand is exerting a force like this in the upward direction. My other hand is exerting an equal force in the downward direction. Is this a couple?
Yes, ma'am.
Is there a difference between my first example and this example?
In first one, acting at same point.
Acting at the same point. Okay, now I'll ask you. This finger is exerting a force like this. Please, you have to imagine. My finger is exerting a force like this. My other finger is exerting an equal and opposite force like this. Now, is this a couple? Is this a couple? This is not a couple. Whether my fingers were touching each other or not touching each other, it didn't really matter. This is not a couple. Then what is a couple? You can say that two equal and opposite forces which are opposed to each other form a couple only if their line of action is not the same. If the line of action is not the same. When I did this, the line was the same. Similarly, when I did this and this also, the line of action of the forces is the same. But then when I applied a force like this and when I applied a force like this, okay, the line of action is not the same. So these two forces can actually turn the object. Only when a force is able to turn an object, you say it is a couple. Are you able to understand this difference now?
Yes, ma'am.
Okay, so just don't blindly say that two equal and opposite forces form a couple. They should be equal and opposite, but then the line of action should not be the same. If the line of action is the same, they cannot rotate the body. If they are going to act like this, then a body placed in between can be rotated. Only then it is a couple. Okay, so now look at this. These two forces are equal and opposite, but they are not forming a couple. Their line of action is not the same, which means they can actually turn the dipole. They can exert a torque on the dipole. And about this center, if this is the center of the dipole, then this distance is going to be d by 2. This distance is going to be d by 2. So there is a force F working at d by 2 from the origin. There is a force acting at d by 2 from the origin. So as a result, what happens is they will turn the dipole. The dipole is initially like this, but then because of the torque, it will turn the dipole. And what will it do? It will turn the dipole and make the dipole parallel to the electric field. Did you understand this? And turning effect of a force is called a torque. Turning effect of a force is called a torque. Therefore, you can now conclude that there will be a net force is 0, but there will be a net torque acting through the center of the dipole in such a way that it will turn the dipole and make it parallel to or it will orient the dipole parallel to the electric field. Initially, it was making an angle theta. And you know what is tau. Tau is equal to, or let us look at what is going to be the torque in this case. In the first case, it's going to be d by 2. Then you have E. F is Q into E. Then you have sine theta. Similarly, for the other also, you will have d by 2 Q E sine theta. Now, if you add up, you're going to get Q d E sine theta. Now, what is Q into E? Q into E is P. So, it will be P E sine theta. Okay, so that will be the net torque. And you know that P is a vector and E is a vector. So, you can write it as P cross E. Is that fine? Therefore, you can conclude that whenever a dipole is placed in a uniform electric field, then the dipole will experience a torque tending to rotate the dipole in alignment with the electric field. So this is your equation. Okay. Now this has got a very nice, okay. So that means if something is turning a body means there is a work done. something is turning a body, that means there is a work done. So who is doing this work? This work is done by the external field E. So let us say that initially let the angle be some theta naught, and let us say that it is turning so that the angle is some theta. Okay, then the work done is going to be equal to minus theta naught to theta tau d theta. In case you're wondering from where this comes from W is equal to integral f dot ds for linear motion. So that in the case of rotational becomes tau dot d theta. And in the next step, this is from the initial angle to the final angle. And you are going to find that there is a minus coming here the minute you are going to remove this vector symbol. This minus is coming because the torque is going to make theta small. The job of tau is to make the angle small. In that sense, tau and d theta are going to be acting in opposite directions. According to vector terminology, so that's the reason why you will have a minus coming here. Okay, so therefore the work done is minus theta naught to theta tau d theta. And just now we have seen what is tau. Tau is PE sine theta. So let's just take out P and E outside the integral. So if you differentiate this, you're going to get minus PE cos theta minus cos theta naught. So this will be the work done. At the same time, you also know that work done is equal to negative of the change in potential energy. Negative of change in potential energy means U initial minus of minus, therefore it becomes 1 sec. Minus of U final minus U initial, that is what is the representation of change. Or I can write it as UI minus UF. That is your work done. Okay, or from this, now look at this, I just wrote this equation and now I'm writing this. So from both this, you can come to the conclusion that potential energy for any theta is simply going to be PE cos theta, or it is P dot E is going to be P dot E, and there will be a minus sign also, P dot E with a minus sign. Okay? And in case you're wondering why that came, I'll just tell you. If you take theta naught is 0, theta naught is 90, you know, cos 90 is 0. Okay, you can take that as the reference. Okay, with respect to that, any other theta, the potential energy for that configuration is going to be minus PE cos theta, which is equal to minus P dot. And you see here, when will U be a minimum? U will be a minimum when P and E are parallel. And U will be a maximum when P and E are anti-parallel. When I say parallel, you see here, when P and E are parallel means cos 0. Cos 0 is 1. Therefore, U will be equal to minus PE. Whereas U max will be P into E because the angle is 180 degrees. And you all know that from mechanics, you know that minimum potential energy means maximum stability. So a system will be stable when the potential energy is a minimum, or when the dipole is parallel to the field. Okay, so you can actually, you know, have some use for this part of physics. So this is the principle behind microwave cooking. I don't know how many of you know it, but then in microwave cooking, the most essential thing is the presence of water molecule. I've been telling you from the beginning of this chapter that H2O is a dipole. It's a dipole. So what happens in microwave cooking is, there is an electric field. Maybe I'll just go to that page of that book, page number 601. Page number 601, I'll just read out. Okay, a water molecule has an electric dipole moment. In microwave cooking, what happens is the electric field of the microwave rotates the dipole moment of water. Now, what happens is, I hope you know what is the AC field. What is the AC? AC field? A field where the direction is changing. Okay, now the microwave AC field will have a frequency of 5 into 10 to the power of 9 hertz. Do you know what this means? 5 into 10 to the power of 9 hertz means what? Are you reading this? The electric field is an AC field. It will keep on changing direction. Okay, alternating field. So the field will change direction 5 into 10 to the power of 9 times per second. That's pretty fast. Okay, so what happens in your material, the food material, is there will be a lot of dipoles like this. A lot of dipoles will be there, and these dipoles each time try to follow the direction of the electric field. So they orient themselves in the direction of the electric field, but that instant is the electric field changes direction. So what happens is these water molecules are keeping track of the moving, of the changing electric field. So they keep oscillating. It's an oscillator motion finally. The water molecules will start oscillating about 5 into 10 to the power of 9 times per second. Isn't it tremendous energy? So it is that vibrational energy which gets passed on to your food, and your food is getting cooked. Is this point clear? Yes or no?
Yes, ma'am.
Yeah. Who said that?
Akshara, ma'am.
Akshara. Akshara, can you in 2 sentences explain microwave cooking?
Ma'am, when water is sprinkled on the food stuff, since it's a
You don't
dipole,
have to, one sec, you don't even have to sprinkle. Sometimes, you know, your bread, for example, you don't put water. There are some water molecules. If any food is having some water molecule, that is enough. Okay, go ahead.
so since water molecule is a dipole, it always has a tendency to orient itself to the field direction.
Hmm.
So since the microwave field changes at a frequency of 5 into 10 power 9 hertz, water molecules also oscillate at that rate per second, due to which the food will be cooked. That energy would be passing through the food.
That's right. This vibrational energy is going to the food and the food gets cooked. So that's clear, I suppose. You told that very nicely. So I'm sure others also must have understood. If they have not understood what I said. Okay, now let's just quickly work out one last problem. With this, we are winding up the chapter. So a molecule of water vapor has an electric dipole moment 6.2 into 10 to the power of minus 30 coulomb meter. This okay. Now, how far apart are the effective centers of the positive and the negative charge in a molecule of H2O? So this is your oxygen, and these are your H. Okay. Now, if you see the number of protons will be equal to number of electrons will be equal to what for H2O? Anyone? How many electrons will be contributed by the oxygen? Chemistry, 8. It will contribute 8 electrons and protons. Hydrogen will contribute 1 each. Therefore, the total number of electrons will be equal to 10. Number of protons also will be equal to 10. This is not actually an accurate model. Chemists will never agree with this model, but then physicists will go with this model that there is a plus 10Q, 10E, E stands for charge of an electron or proton. 10E separated from a negative 10E by a distance D and gives rise to P is equal to Q into D. Did you understand? Electrons will have one electron each participating. Then you have your oxygen will have 8. So 8 plus 1 plus 1 is 10. So this is the way we are taking the calculation. So now P is given to you. So can you get your D? So D will be equal to P by Q. So P is given to you as 6.2 into 10 to the power of minus 30 divided by Q. Q is going to be 10 into the charge of an electron or a proton, 10 to the power of minus 19. So you get your answer for D. Okay, but physics people only will agree with this model. If you go and tell this model to a chemistry person, they will beat you and give you 0 marks because the physics model is wrong. The total electrons and protons are not going to come out like this and behave like two bundles with a distance d. This is just a model used by physicists. It is wrong. Okay, it's okay to work out a problem at your level, but don't go and tell this to any chemistry person. Okay, next. What is the maximum torque on a molecule of water in a typical laboratory electric field equal to 1.5 into 10 to the power of 4 Newton per Coulomb? If P is already given to you, what is the value of P given? P was given to you as 6.2 into 10 to the power of minus 30. 6.2 into 10 to the power of minus 30 Coulomb meter is your P value. Now you have to find out what is going to be the maximum torque. Maximum torque. What is the maximum torque? When will the torque be maximum? What is tau first of all? What is tau? Tau is equal to P cross E. P cross E, which is, if I talk about modulus, it's going to be tau is equal to P E sine theta. So when will tau be a maximum? Tau will be maximum when sine theta equal to? Sine theta equal to 1. When will sine theta be equal to 1? When theta equal to? When theta equal to 90 degrees. When theta equal to 90 degrees, that is when the torque is going to be a maximum. If on the other hand, your electric field is like this and your P is also like this, will there be a torque? Sine 0. So no torque. Okay. So maximum torque is P into E. You can always substitute and get the answer. Next thing. How much work is done by the electric field in rotating the molecule into alignment with the field? If it is initially pointing in a direction opposite to the field. What is the meaning of that? What is the work done in aligning the dipole parallel to the electric field, assuming that initially it is anti-parallel to the field? How will you do this? Remember this? Few minutes back we wrote. Work done equal to change in, minus of change in potential energy we wrote. And we wrote it as minus of P E cos of theta minus, yeah, because there is a minus, you can simply say that cos of theta naught minus cos of theta, which is PE cos theta minus cos theta naught. Right. So now put it here. So PE into cos of theta. Cos theta is 1 minus of cos of theta naught. If theta equal to 0, and theta naught equal to 180 degrees. Then what is cos 180? Minus of minus 1. So it is 2 times P. Substitute, get your answer. Okay? In case you still have any doubts, I'll just write one more step. W equal to minus delta U, which is minus of U final minus U initial. Okay? And you know that the expression for potential energy is minus P dot E. So this is what we have used. Okay, so with this we are winding up this chapter. Anything you want to ask? If nobody has anything to ask, I'll just wind up. And what I'll do is the PDF of this, I will maybe by today evening, I'll put it for you people. You can just take it and use it. So that way 2 chapters are done with. Now we have to start with Gauss law in the next class. Okay? If there's nothing to ask, I'll stop. So people can leave. Good day then. Uploading this video.
Thank you.
I put access. Oh, attend. Kaladhar, you better attend.